This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 27, Molecular Symmetry. I recommend you to use this website, simorder.org, to study the symmetry elements, symmetry operations, and point groups of molecules. And I recommend you to watch some videos on symmetry in this playlist. I made this playlist for teaching inorganic chemistry. And molecular symmetry is one of the most important topics in inorganic chemistry. But in this class, in this video, I'll just briefly introduce you to the point groups, the character tables, and the multiplication table. Over here, this is a flow chart to determine the point groups. I'll give you a simple example, water, H2O. So first, is water linear or not? Not linear. And then, does water have two or more CN axes? No. We go here. Do we have a CN axis? Yes, we have a C2 axis. And then, do we have two other C2 axes perpendicular to the principal C2? No. Do we have a sigma H? Sigma H is a symmetry plan that's perpendicular to the principal axis. No, we don't have it. Do we have two sigma V? Yes, we do have two sigma V's. They both contain the principal C2 axis. So yes, C2V, that's water. Ammonia, not linear, we go here. Two or more CN? No, we have only one, C3, so we go here. All right, and then C3, yes. Do we have three C2 axes perpendicular to the principal axis? No. Do we have sigma H? Again, sigma H is the symmetry plane perpendicular to the principal axis. No. We go here. Three sigma V's? Yes. C3V. What if you have a linear molecule, HCl? Linear? Yes. Inversion center? No. C infinite V point group for HCl, hydrogen chloride. What if you have hydrogen 2? Linear? Yes. Inversion center? Yes. It's D infinite H for H2. So heteronuclear molecules, C infinite V. And if you have homonuclear diatomic molecules, it's D infinite H. And over here, there are also some highly symmetrical molecules. We'll talk about those examples. Okay, again, linear molecules, it's really easy. Highly symmetrical molecules like carbon-60, that's IH point group. SF6, octahedral structure, OH point group. Methane, TD point group. Some molecules have really low symmetry, like this one is C1 symmetry. Carbon bonded to hydrogen, fluorine, chlorine, and bromine. 4 different functional groups, it's C1 symmetry. And over here, this molecule is planar, so it has a planar symmetry CS. And then this molecule has inversion center, CI point group. All right, so it has to be staggered conformation. All right, so this carbon is bonded to HF chlorine. This carbon is also bonded to HF and chlorine. And then look at these two groups, C groups versus D groups. The difference between C groups and D groups is this. In D groups, you have N C2 rotation axes that are perpendicular to the principal rotation axis. And in C groups, you do not have such C2 rotation axis. All right, let's look at a few examples. Benzene D6h. The principal axis is this C6 rotation axis. And there are 6 C2 rotation axis perpendicular to this principal rotation axis. And also you have D3H. This is ethane eclipsed conformation. You have D2D allyne structure. If you have my lecture notes, you can just do Control-click to see this molecule. And ethane staggered belongs to this D3D point group. Over here in this point group, you do not have sigma H symmetry plan, but you do have sigma D symmetry plan and D2 twisting. So in this case, you do not have any symmetry plan. Again, you can do Control-click to see this molecule. C groups do not have those C2 rotation axes perpendicular to the principal axis. For example, ammonia, water, They are C3V or C2V. And over here, this C2H with a sigma H symmetry element, the trans, this one trans. So if you look at this trans structure, you can see there's a C2 going through the center, and there's a sigma H perpendicular to this C2. This H2O2 hydrogen peroxide, this is a non-planar structure. It has a C2 symmetry element. And then S2N groups, well, this kind of molecules are rare. So here's one example. You can see this molecule has a very unusual structure, and it does have a S4 symmetry element. That means you can rotate this 90 degrees, followed by a reflection. Okay, so this is S4. Now let's look at the character table for the C2V point group. For example, water belongs to C2V point group. Now let's look at this point group. First, I want you to look at this 1, 2, 3, 4 columns. They correspond to the 4 symmetry classes. And then A1, A2, B1, B2, those are 4 irreducible representations. What about these numbers? 1, 1, 1, 1 are the characters of this A1 irreducible representation or A1 symmetry species. 1, 1, negative 1, negative 1 are the 4 characters of this A2 symmetry species or irreducible representations. So this row is B1, this row is the characters of B2. Now, what about these 2 columns? Okay, this column first. X, Y, and Z, they refer to the translations in the X, Y, and Z directions. Rx, Ry, Rz are the rotations. So we can easily tell the symmetry species of X, Y, and Z are B1, B2, and A1. What about rotations? About the X, Y, and Z rotation axis, it's B2, B1, and A2. All right, and on top of that, X, Y, and Z also give you the symmetry of the p orbitals. So px, py, and pz have this b1, b2, and a1 symmetry. So similarly, over here, it tells you the symmetry of the d orbitals. So if you have d orbitals in a molecule that belongs to this C2V point group, and then dxy is a2 symmetry, dxz is b1 symmetry, dyz is b2 symmetry, dz squared is a1 symmetry. What about dx squared minus y squared? It's a1 symmetry. So x squared and y squared are both a1 symmetry, so the linear combination of these two, including x squared minus y squared, is a1 symmetry. So this is the character table. Oh, and I forgot to mention this will also give you the symmetry of the components in the matrix of polarizability, which is useful for you to determine whether a Raman transition is allowed or forbidden. X, Y, and Z are also the symmetry of the X, Y, and Z components of the electric dipole moment. It helps you to determine if an infrared transition is allowed or forbidden. Now let's look at the product table. So the product table or the multiplication table is pretty simple. What you need to do is you need to multiply these 4 numbers and these 4 numbers respectively, and you get 4 new numbers. All right, so 1 times 1 is 1, negative 1, negative 1, that's 1. 1 times negative 1 is negative 1. Negative 1 times negative 1 is negative 1. So if you do this 4 multiplications, you get a 1, 1, negative 1, negative 1. That happens to be the 4 characters of the A2 symmetry species. So B1 times B2 is A2. B1 times B2 is A2. All right? And what about B2? B1 times B2? It's the same thing. It's the same thing. Okay, so you probably realized that A and B are referring to this symmetry versus anti-symmetry with respect to the rotation, right? C2 rotation. 1 and 2 are referring to symmetry versus anti-symmetry with respect to this reflection, right? 1, negative 1, all right? So A and 2 are referring to symmetry versus anti-symmetry. A and B are referring to symmetry and anti-symmetry. And then that will help you to build this product table easily. So A times A is got to be A. Symmetry times symmetry is symmetry, right? A times B is got to be anti-symmetric, right? Symmetric, anti-symmetric. You multiply this two, you've got to get anti-symmetric, all right? And 1 times 1 is 1. 2 times 2 is also 1, all right? So B2, that's why B2 times B2 is A1, because B times B is A, and 2 times 2 is 1. Why? So 1 and 2 are not really numbers. 1 and 2 are referring to symmetry, symmetric versus anti-symmetric after this operation with respect to this sigma v plane, all right? So 1 and 2 really means symmetric and anti-symmetric with respect to a reflection via this through this symmetry plane, right? So that's how you build this product table. Again, A times A is A. B times B is also A. A times B is B. B times A is B. 1 times 1 is 1. 2 times 2 is 1. 1 times 2 is 2. 2 times 1 is 2. All right, so if you can remember this, you just remember plus 1 times plus 1 is 1. Minus 1 times minus 1 is 1. Plus 1 times minus 1 is minus 1. Minus 1 times plus 1 is minus 1, because symmetric corresponds to plus 1. Anti-symmetric corresponds to negative 1. Why is this product table useful when we are looking at the electronic transition or vibrational transition induced by a photon? How do we know it's allowed or forbidden? We need to define a concept. It's called transition dipole moment. It's a vector. If this vector is 0, then the transition is forbidden. If this vector is non-zero, then the transition is allowed. And this is a vector. So if one of the three components in the x, y, and z directions is non-zero, then this vector is non-zero. The transition is allowed. So we need to evaluate three integrals. Okay, 1, 2, 3. These three integrals are the three components in the x, y, and z directions for this transition dipole moment. If all three integrals are 0, okay, all three are all zeros, the transition is forbidden. But you know it's very hard to evaluate an integral unless if we know the symmetry of each of these three terms. Okay, so this is the initial state. This is the final state. And this is the symmetry species of the electric dipole moment. And we can look up the symmetry species of mu x, mu y, mu z. They are here. Mu x, B1. Mu y, B2. Mu z, A1. So the three components of the electric dipole moment of a C2V molecule has the following symmetries: B1, B2, and A1. All right? And what about this psi sub m and psi sub n? They are the wave functions of the initial state and final state. If you're talking about electronic transition, psi sub m and psi sub n are referring to the electronic states. But if you're talking about vibrational transition, psi sub m and psi sub n are the vibrational states. Okay, so different kind of wave functions. But in short, you just need to look at the three integrals and to see if they are 0 or non-zero. So really, there's a shortcut for you to determine whether this is 0 or non-zero. You find the symmetry of the initial wave function, the symmetry of the final wave function, the symmetry of this electric dipole moment, and then you do the multiplication. All right, using this table, like B2 times A1 is B2, and then B2 times A2 is B1, something like that. And if the product is A1, you have a non-zero integral. If the product is not A1, then the integral is 0. All right, so I'll give you a more solid example for a real molecule a bit later. So again, you need to look at the product of the symmetry species of 1, 2, 3 terms. All right, if it's 0, okay, that means, well, forbidden in the x direction. If this is also 0, forbidden in the y direction. If this is also 0, forbidden in the z direction. If all 3 are zeros, then the transition is forbidden. If one of the 3 is non-zero, then the transition is allowed. Okay, so now let's look at a real example. Let's look at a formaldehyde. Let's look at a electronic transition. Of course, you can look at vibrational transition as well, but let's look at the homo-LUMO electronic transition for now. Let's look at the MOs of formaldehyde. 1, 2, 3, 4, 5, 6. This 6 orbitals are occupied. This one is unoccupied. This is the HOMO. This is the LUMO. 1, 2, 3, 4, 5, 6. All right. So the HOMO has a B2 symmetry. The LUMO has a B1 symmetry. All right. So this is the HOMO B2 HOMO. LUMO B1 symmetry, right? And what's in the middle? In the middle, B1, B2, A1. Where did I get this B1, B2, A1? Those are the symmetry of the X, Y, and Z components of the electric dipole moment. B1, B2, A1. Okay? X, B1, Y, B2, Z, A1. B1, B2, A1. So they're here, B1, B2, A1. And then you just need to use the product table to get the product of this 3 symmetry species. Actually, you can just, view this B's as -1. So -1, -1, -1. The result is -1. So it's B. 2, 1, 1. 2 is -1, 1, 1. They are positive 1. So the result should be -1. That's 2, B2. So this B means anti-symmetric with respect to rotation. This 2 means anti-symmetric with respect to a reflection. All right. Similarly, you get this B times B times B is B. 2 times 2 times 1 is 1, because this 2 and this 2 are referring to anti-symmetric. Okay, they're not numbers. Okay, you don't say 2 times 2 is 4 here. Over here, 2 means anti-symmetric with respect to a reflection. So anti-symmetric times anti-symmetric, it's symmetric. So in here, 2 times 2 is 1. 1 times 1 is 1. All right. So the result is B2. Over here, the result is B1. Over here, the result is A2. None of these 3 species is A1. None of these 3 integrals is non-zero. So all 3 are zeros. That means the electronic transition from HOMO to LUMO is forbidden. So from here to here, it's forbidden. All right, I want to be more clear. Actually, I'm talking about photon-induced transition from HOMO to LUMO is forbidden. All right? So if you have enough thermal energy, well, it's still allowed. But I just want to let you know, if you take the UV vis spectrum of this formaldehyde, you're not going to observe this HOMO to LUMO transition on the UV vis spectrum because it's forbidden. Now I just want to show you a more complex character table for a more symmetrical point group. This is D6H. One example is benzene. There are 12 symmetry classes, and you have 12 irreducible representations. All right, and similarly, each row is the 12 characters. Okay, associated with the corresponding irreducible representation, or you may call this symmetry species. And again, X, Y, Z are the translations. RX, RY, RZ are the rotations. And also X, Y, and Z are the symmetries of the PX, PY, PZ atomic orbitals. So if you ask me, PX, PY, PZ, what are the corresponding symmetry species? X and Y are doubly degenerate, E1U, and Z is A2U. All right. They are both. They are all U symmetry. U symmetry means anti-symmetric with respect to the inversion center. Over here, those are d orbitals. Okay, those are d orbitals. So you know the symmetry of dxy and dx squared minus y squared. They are doubly degenerate. It's e2g. xz, it's e1g. And then dg squared, it's a1g. And also, if you look at those quadratic functions, they give you the symmetry of the components of the 3x3 matrix of polarizability. X, Y, and Z, they give you the symmetry of the X, Y, and Z components of the electric dipole moment. All right, so if you have benzene, if you're looking at the electric transition of benzene from HOMO to LUMO, you need to find the symmetry of HOMO, the symmetry of LUMO, and then you need to find the symmetry species of this X, Y, and Z components of the electric dipole moment. And again, similarly, you need to evaluate this three multiplications if the resulting product is not totally symmetric, okay, and then you get a 0. If you get all zeros in all three directions, the transition is forbidden. But in my vague memory, I think HOMO to LUMO for benzene is allowed, but correct me if I'm wrong. Now let's look at the product table for this D6H point group. It gets more and more complicated, especially when you have degenerate, doubly degenerate character table. So in this case, it's just 2 times 2, you get 4. 1 times 1, negative 1, 1. Negative 2 times 2, negative 4. And then 0, 0, 4, negative 1, 1, negative 4, 0, 0. So this is E1U times E2U. That's how you deal with this. All right, you get this. And you need to decompose this. I'm going to say this is a vector of 10 numbers. You're going to decompose this into some other vectors. And actually, if you look at the result, okay, let's look at the result. E1U times E2U. E1U times E2U. Okay, you get B1G plus B2G plus E1G. All right, so you get actually, I'm going to write it here. You get a B1G, you get a B2G plus E1G. All right, why is that? So E1U times E2U, why do we get B1G plus B2G plus E1G? All right, I'm going to just verify this, all right? I'm going to verify this. So first, I'm going to add up B1G and B2G and E1G. Over here, and this, you get 4, right? You get 4. So I'm going to write this number 4 somewhere, maybe on top of this 4. Okay, I'm going to add up these 3 numbers, negative 1. I'm going to add up these 3 numbers, positive 1. These 3 numbers, negative 4. These 3 numbers, 0. These 3 numbers, 0. These 3 numbers, 1, 1, 2, that's 4. These 3 numbers. Okay, somehow it just disappears. It's negative 1. And then these 3 numbers, positive 1. Oh, it just disappears. Anyway, I think you got my point. So if you just add up this 3, okay, this 3, this 3, this 3, this 3, this, you get the same numbers as in the product of E1U times E2U. So really, when you do E1U and E2U, you just need to have this vector and this vector, and then you're going to multiply numbers one by one. Okay, you get 10 different products over here, 10 products. This 10 numbers is exactly the same as the 10 numbers as the sum of B1G, B2G, and E1G. So that's why E1U times E2U is B1G plus B2G plus E1G. All right? Okay, finally, let's look at another example. Let's look at benzene. So the A1G to A1U electronic transition is forbidden. The A1G to A1U vibrational transition is also forbidden. This is because if you look at the electric dipole moment in the x and y direction, it's E1U. So you put E1U there, E1U. And then you do the multiplication. A times A is A, 1 times 1 is 1, G times U is U, and then U times U is G. So the result is going to be E1G, okay? And also E times A is E, okay? E times A is E. So the result is E, okay? A times A is A times E is E. And 1 times 1 is 1, 1 times 1 is 1, so you have a 1 here. G times U is U, U times U is G, so E1G. All right, you get E1G here. E1G, where is E1G? E1G is here. Oh, E1G is here. Okay, E1G is here. E1G, right here. This is E1G. Okay. What about the Z direction? Z direction, the electric dipole moment in the Z direction has a to U symmetry. Z direction, A to U symmetry. All right, A to U. So also you do the product A1G times A2U times A1. It's A2G. All right, it's A2G. So neither E1G nor A2G are totally symmetric. That means these two integrals will be 0. This integral will also be 0. That means the transition dipole moment for the photon-induced A1G to A1U electronic transition or vibrational transition is forbidden.